Welcome to Undamped Forced Spring Mass Systems. So again, recall a spring mass system has displacement modeled or displacement from equilibrium. Modeled by my double prime plus cy prime plus ky equals f, with m the mass, c equals the damping coefficient, k equal to the spring constant, and F the external force. In an undamped forced spring mass system, essentially the damping coefficient is 0. There is no damping force. So in an undamped forced system, the damping coefficient is 0. So we are looking at the equation, or we have the equation y double prime plus ky, my double prime plus ky is equal to f, or y double prime plus k over m y is equal to f over m. So we still have a way of finding k over m, but since m also is dividing force in this case, we now do need to know mass to actually get the precise function. We're going to work more generally to start off. So let's consider a spring mass system with no damping force and an external force of f of t equals f naught times cosine of omega t, with initial displacement 0 and initial velocity 0. And our job is to find the displacement at time t. So our IVP we are looking at y double prime plus k over m times y is equal to f naught over m times cosine of omega t. Right? If we divide the original equation by m, we wind up with our force divided by m on the right. And then we have y of 0 is 0, and y prime of 0 is also 0. So this is our IVP. So anytime we want to go about solving such an equation, we need to find the general solution first. We'll start off with finding the homogeneous general solution. So once again, I'm going to set omega naught to be k, the square root of k over m. So we are looking at y double prime plus omega naught squared y is equal to f naught over m times cosine of omega t. The homogeneous component, our homogeneous equation, the right-hand side is just 0. So we're looking at y double prime plus omega naught squared times y equals 0. This has characteristic equation y r squared plus omega naught squared is equal to 0. So we get, once again, r is plus or minus I times omega naught. And so our homogeneous solution, our homogeneous general solution, is y is equal to C1 times cosine of omega naught t plus C2 times sine of omega naught times t. When we go to find our right-hand side, it's up to you. So since the right-hand side is fairly simple, I might use method of undetermined coefficients. So next up, we're going to solve for a particular solution. And again, since the right-hand side is simple, let's just use method of undetermined coefficients. Turns out that we will have two cases here. So since our general homogeneous solution has cosine omega naught t, and our forcing function has cosine omega t, our guess will be different depending on if omega equals omega naught or not. So we'll go ahead and do case 1. We'll look at the case where omega is not equal to omega naught. Then we can use our guess simply to be yp is equal to a cosine of omega t plus b times sine of omega t. We have yp prime as negative a omega times sine of omega t plus b omega times cosine of omega t. And the second derivative, we would have negative a times omega squared cosine of omega t plus b times, or sorry, minus so minus b times omega squared sine of omega t. If we plug this into our equation, so yp double prime plus k over m times yp equaling f naught over m times cosine of omega t becomes, we would have negative a omega squared cosine of omega t minus b omega squared sine of omega t, then plus k over m times a cosine of omega t plus b sine of omega t. And this should all equal f naught over m times cosine of omega t. So what we have then is that this, that right-hand side also has a plus 0 sine omega t. So if we match our cosine terms, cosine coefficients, we have a negative a times omega squared and a plus k over m times a, all multiplying our cosine omega t. So that should match f naught m over m. So we get that negative a times omega squared plus k over m times a. This should equal our f naught over m. And then similarly, the second component, negative b omega squared and a plus b times k over m should match our coefficient of 0 for sine. So we have a negative b omega squared plus a k over m times b should equal 0. So if we go about factoring out our a, we're looking at a times k over m minus omega squared equals f naught over m. And so we get that a should equal f naught divided by m, and then still in the denominator multiplied by k over m minus omega squared. Or a is f naught over k minus m times omega squared. Versus for b, if we factor out a b, we are looking at b times, in parentheses, k over m minus omega squared equaling 0. And if omega is, again, for here, omega is not the square root of k over m, so we're good. We just, in this case, get b equals 0. So we wound up with particular solution. So our general solution or first we have our yp is f naught over k minus m times omega squared, all times cosine of omega t. Our general solution, therefore, is y is equal to f naught over k minus m times omega squared cosine of omega t plus c1 times cosine of omega naught t. Plus c2 times sine of omega naught t. I just realized we can change a little bit here. K over m was omega naught squared, so I'm just going to fix that quickly. So k over m was omega naught squared. So we can write this as an omega naught squared. So we have, again, this becomes, instead of k over m, we can swap it out with omega naught squared. Swap with omega naught squared. Swap with omega naught squared. And so we can just leave this as m times omega naught squared minus omega squared. This may be better since we already rewrote the problem with omega naught. And our particular solution, again, will have f naught over m times omega naught squared minus omega squared. And in our general solution, again, we have m times omega naught squared minus omega squared. So this is our general solution. Again, here we were assuming that omega was not equal to omega naught. We could plug in our initial conditions. So y of 0 is 0 and y prime of 0 is 0. What we get then is that y of 0 would be f naught over m times omega naught squared minus omega squared times 1 plus c1, and then the rest would become 0. Update my screen. So we have that this is equal to 0, and therefore c1 is just negative f naught over m times omega naught squared minus omega squared. Y prime should be equal to, we would have a negative f naught times omega over m times omega naught squared minus omega squared times a sine of omega t. Then we would have a minus c1 times omega naught times sine of omega naught t. And then we would have a plus c2 times omega naught times cosine of omega naught t. So if we do y prime of 0, those first two terms just disappear. That's just c2 times omega naught. This is equal to 0. And we get that our c2 is just 0. So we wind up with our solution of y is equal to f naught over m times omega naught squared minus omega squared times the cosine of omega t. And then we have minus f naught. Actually, I'm going to put this in parentheses. That becomes minus just 1 times cosine of omega naught t. And so the coefficient in front of the cosine omega naught t was the same as the coefficient in front of cosine omega t, except for a negative. So if we factor that out front, we just have cosine omega t minus cosine omega naught t. And so we get this as our ultimate solution in the case where omega is not equal to omega naught. And then from here, we can do some manipulation to get it into a different form. With a little trig manipulation, it turns out that this can be rewritten in the form y is equal to r of t times sine of omega naught plus omega over 2 times t, where r of t is 2f naught divided by m times omega naught squared minus omega squared times sine of omega naught minus omega over 2 times t. So a reason for writing it in this form is if we view the sine of omega naught plus omega over 2 times t as our primary function, and that r of t as sort of our amplitude at any given point, then we have sort of our background function, our background sine function. And then we have oscillations taking place within that. Sorry. That should stay this way. hard to draw in here. So we have sort of our oscillation should have stay within. I apologize for the sloppiness of that. So we wind up sort of with like 2 layers of oscillations going on. I apologize for the sloppiness of that. In our next video, we'll look at case 2. So case 2 with omega equal to omega naught, we'll look at in the next video.